Welcome to my channel, Worldwise. Am I the only one that didn't know the mind-boggling truth about light speed? We often hear that the speed of light is about 299,792,458 meters per second. That's incredibly fast. It's so fast, in fact, that it can circle the Earth more than 7 times in just 1 second. It's the fastest anything can travel in the universe. Nothing else even comes close to matching this speed. But there's a fascinating detail that often gets overlooked. It's something that challenges our understanding of this cosmic speed limit. That number, my friends, is merely an average speed. Think about it. When we say light travels at this speed, we're talking about an average over a round trip. We've measured how long it takes light to travel to a distant mirror and back. This round-trip measurement is what gives us that famous number. But what if light travels at a different speed in one direction compared to the other? What if the speed of light isn't constant in both directions? What if the journey to the mirror is slower than the return trip, or vice versa? This asymmetry could change everything we think we know. Our measurements wouldn't be able to tell the difference. The round-trip time would still give us the same average speed. This is where the mystery of the one-way speed of light begins. It's a question that has puzzled scientists for generations. Measuring the true one-way speed of light is much trickier than it seems. It requires incredibly precise instruments and innovative methods. But before we dive into that, let's rewind the cosmic clock and explore the earliest attempts to understand light's incredible speed. From ancient astronomers to modern physicists, the quest to measure light speed has been a journey of discovery and wonder. Long before we had the technology to measure light speed accurately, the great Galileo Galilei suspected that light didn't travel instantaneously. He devised an ingenious experiment to test his hypothesis. Imagine Galileo and his assistant standing on distant hilltops. Galileo would uncover a lantern, and the moment his assistant saw the light, they would uncover their own lantern. By timing how long it took for him to see the return flash, Galileo hoped to calculate the speed of light. Alas, even with the most meticulous measurements, Galileo couldn't detect any delay between uncovering his lantern and seeing the return flash. Light seemed to travel far too quickly for his experiment to capture. He concluded that light's speed, if not infinite, was at least incredibly fast. While Galileo didn't succeed in measuring the speed of light, his experiment laid the groundwork for future scientists who dared to unravel this cosmic mystery. Fast forward a couple of centuries, and enter French physicist Armand Hippolyte Louis Fizeau, a pioneer in the field of optics and light measurement. In 1849 he achieved a groundbreaking feat, measuring the speed of light with remarkable accuracy for the time. This was a monumental step forward in the world of physics. His secret weapon, a spinning toothed wheel, and a brilliant idea that would change our understanding of light forever. Fizeau's setup involved a beam of light aimed at the edge of a rapidly rotating toothed wheel. This ingenious setup was both simple and effective. As the wheel spun, the light would alternately pass through a gap between the teeth and be blocked by a tooth. This created a series of light pulses. These pulses of light traveled towards a distant mirror, which was positioned several kilometers away. The distance was crucial for the accuracy of the experiment. The reflected light pulses would then travel back towards the wheel, completing the round trip. By carefully adjusting the wheel's rotation speed, Fizeau found the sweet spot where a returning pulse would always hit the next gap in the teeth. This precise tuning was key to his success. By knowing the distance to the mirror, the number of teeth on the wheel, and the rotation speed, he could calculate the speed of light. This calculation was a remarkable achievement for its time. His result? Astonishingly close to the currently accepted value. Fizeau's experiment was a testament to human ingenuity and the relentless pursuit of knowledge. However, it's crucial to remember that Fizeau's method, like all subsequent methods, still measured the two-way speed of light, the average speed to the mirror and back. This distinction is important in the broader context of light speed measurements. Section 4. Average speed versus one-way speed, a tale of two journeys. Let's imagine a car making a round trip. It travels the first leg of the journey at 60 miles per hour, and the return leg at 40 miles per hour. If we calculate the average speed for the entire trip, we get 50 miles per hour. But notice that the car never actually traveled at 50 miles per hour at any point during its journey. The speed of light presents a similar conundrum. We know the average speed over a round trip, but what if light, like our hypothetical car, doesn't travel at a constant speed. What if it speeds up or slows down depending on the direction? Measuring this one-way speed is where things get truly mind-boggling. Section 5. Einstein's revolution: light, space, and time. In the early 20th century, Albert Einstein revolutionized our understanding of space, time, and light with his special theory of relativity. One of its groundbreaking postulates was that the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This might seem counterintuitive. Imagine chasing after a beam of light at half the speed of light. You might expect the light to appear to be traveling slower relative to you. However, Einstein's theory states that even as you chase after it, light will always appear to travel away from you at the same constant speed. Einstein's theory had profound implications for our understanding of light's speed. It suggested that space and time themselves warp and adjust to ensure that the speed of light remains constant. Section 6. The uncharted territory: measuring the one-way speed of light. So, how do we measure the one-way speed of light if it always seems constant? This question has puzzled scientists for decades and remains one of the most intriguing challenges in physics. This is where things get tricky. The concept seems simple, but the execution is anything but straightforward. To measure the one-way speed, we'd need two synchronized clocks, one at the starting point and one at the end point of the light's journey. These clocks must be perfectly synchronized to ensure accurate measurement. We could then send a pulse of light and time how long it takes to travel between them. This sounds simple in theory, but the practicalities are far more complex. However, synchronizing these clocks without relying on the speed of light itself proves to be an insurmountable challenge. This is because any synchronization method we use is inherently dependent on the very speed we are trying to measure. Any method we use to synchronize the clocks, be it radio signals or physical transportation of the clocks, would itself be limited by the speed of light. This limitation creates a paradox that is difficult to overcome. This creates a fascinating circular problem. The very act of trying to measure the one-way speed of light is hindered by our current understanding and limitations of physics. We need synchronized clocks to measure the one-way speed of light, but synchronizing those clocks requires knowing the one-way speed of light in the first place. This conundrum continues to challenge and inspire physicists around the world. Section 7. Light speed in our modern world: trusting the average. Despite the mysteries surrounding the one-way speed of light, our modern world relies heavily on the constancy of its average speed. GPS navigation, fiber optic communication, even the timing of traffic lights. All these technologies function flawlessly based on the assumption that the average speed of light is constant. Perhaps someday, we'll devise an ingenious method to definitively measure the one-way speed of light. Until then, the universe holds on to its secrets, reminding us that even in the vast expanse of space and time, some mysteries continue to captivate and inspire our curiosity. Check out my next video now!